Thanks, Julian, for the introduction. Hi, everyone. My name is Jiarong, and I'm glad to be here virtually. This is my first DRAKKAR workshop. I hope you are not saturated with all the discussions. So today we are here, and I'm going to talk about my postdoc work as a postdoc at NYU, working with mainly LoRa as part of a LEAP NM square line project. It's on the topic of air-sea flux parameterization. So we all know that air-sea interaction is important, and it's mainly through the exchange of fluxes. So the momentum flux, the wind stress and the surface heating and cooling from the atmosphere drive the ocean circulation, and the evaporation and heat flux from the ocean in turn influences the atmosphere, and this gives rise to major modes of variability and extreme events, etc. So it's really important for us to accurately quantify these fluxes in our coupled ocean atmosphere model. And in this talk, I'm mostly concerned with the turbulent fluxes, so the momentum flux and the latent and sensible heat flux. There's another part of heat flux that's short and long wave radiation that is not directly investigated with this data-driven method, but is also important. So these turbulent fluxes, they are given by the vertical transport of the fluctuation in the atmospheric boundary layer. So when we look at the air-sea interface, it's actually two coupled boundary layers with a freely evolving interface, made with waves, etc. But in our coupled model, due to the coarse resolution, usually the surface, the very surface layer of the atmosphere consists only one grid cell. So all of these fluctuation and the transport needs to be parameterized. Yeah, so it's like within this area where we have the largest gradient that we don't have any resolution. And so these transport due to the covariance of the vertical fluctuation with either the velocity or the scalar quantity, temperature or humidity. These are parameterized, and they're usually computed using this atmospheric boundary layer theory called the Monod-Nabokov similarity theory. And this is basically gives you the self-similar shape of velocity, temperature, and humidity in the boundary layer, and you use that iteratively to get the flux at the surface. Yeah, so if we kind of take that and look at the air-sea flux as a practical algorithm, how people usually call it in a coupled atmosphere-ocean model, basically your inputs will be the surface meteorological and ocean variables. This include your wind speed, atmospheric temperature, humidity at the bottom grid. And from the ocean, you take mostly SST, but sometimes you can also include current. And you pass through the algorithm, and it gives you the turbulent fluxes, the momentum, sensible, and latent heat fluxes. And the bulk formula, which people usually use, are casted as explicit. So it's expressed as being proportional to the wind speed. So this is a magnitude of the wind and the difference of quantities between the atmosphere and the ocean. So velocity, temperature, specific humidity. And this coefficient actually needs to be computed implicitly. And And there are parameters, important ones within the use of von and Hopkov theory, including, for example, the shape of the self-similar shape, the roughness, length, etc., that they need to be empirically fitted to observations. So one of the main motivation for this work is that since these parameters are already fitted, could we learn directly from these observational data and extract a purely data-driven flux algorithm? And yeah, also I'd like to mention that there is an uncertainty in RC flux algorithm, although it's, in my opinion, kind of under-discussed. And so if we take a look at what causes the uncertainty in the output, the fluxes themselves, they come from both uncertainty in the inputs, so the meteorological ocean variables that you pass in, as well as the flux algorithm itself. And there has been a discussion about the kind of relative magnitude between these two source of uncertainty for flux products. And in this figure from EU 2019, it's shown that both these contribute to the flux uncertainty. Here, the different colors are different input sources, and between the dashed and the solid line are if you use different flux algorithm. And this is zonally averaged latent plus sensible heat flux. So we see that there is discrepancy even when you use the same source of input, but different flux algorithms. There's also another work that's another type of work that discusses the uncertainty due to the coarse graining effects. When you're in a coarse model, you know, the inputs are smoothed out, so this will give you a different output of fluxes due to like the a nonlinear relationship between in the flux algorithm. For this, you can check out Julia's work, and this is also not discussed here today. And in this work, we are concerned with the uncertainty in the flux algorithm itself. Okay, so for the data that we are learning from, these are shipborne measurements. So here's the map showing the trajectories of all these cruises. This is a compilation of cruises over the past 30 years or so from NOAA PSL. We have on the order of 10,000 samples, hourly averaged eddy covariance. So basically, they learned, well, they measured the high frequency fluctuation of all these turbulent components, and they computed this eddy covariance with hourly averaging. And these are the data that all the bulk algorithm we use are fitted to. And yeah, unfortunately, we have no high fidelity numerical simulations that are possible yet to give us direct ARC flux across a wide range of conditions. So this eddy covariance data remain our best source for constraining flux algorithms. And also, I want to mention that there are also some buoy data, which we might incorporate later from ocean observation initiatives. But there are a lot of buoys out there that sort of are reference sites for RC fluxes, but they don't measure eddy covariance directly. They only measure the inputs to the surface meteorological inputs. So these are data that we cannot use. And And also one important distinction of this work is that we developed a probabilistic algorithm. What that means is instead of thinking of the algorithm as deterministically giving you an output given the input, we make the output the conditional distribution of turbulent fluxes given the input of the medial ocean variables. And the motivation for doing this is that we know that the air-sea exchange is complicated, and the bulk algorithm uses average quantities in the boundary layer, and also it ignores some important microphysics such as surface waves. So all these input they don't necessarily give you deterministically the output. And also the other thing is if we look at just the observations themselves, they come with their own measurement uncertainty, etc. So it is more of a natural choice to represent the output as some sort of conditional distribution on the input. And so so this is the mathematical framework. So we also made the further simplification that we assume the output is univariate Gaussian when conditioned on inputs. So that means we only need to learn the conditional mean and the standard deviation. And we learn this by minimizing the negative log likelihood loss. So this is basically a maximum likelihood estimate. And so using some pretty small neural network, we learned, so there is separate neural net for the mean and the standard deviation. So, and we learn those for all three fluxes. And the inputs that we ended up using are the wind speed, temperature of the ocean, temperature of the atmosphere, relative humidity, and surface pressure. So this is, I would say, a subset of bulk algorithm, which makes also this calling this our flux algorithm easy because, yeah, if you can just replace bulk algorithm with what we have proposed. And this is a simple demonstration in a 1D input, a 1D output case, how the neural net is able to learn both the mean and the standard deviation simultaneously by minimizing this negative log likelihood loss. So once we have learned this mean and standard deviation, and we can take a look at the statistical score of this proposed neural network. So first, if we just look at the mean, and we can compute its correlation with the observation, so the truth. So this is the R-square score and also the bias, meaning the mean of the difference over the data set between the predicted and the measured. So in terms of R-squared, so first of all, we can see that there is some level of improvement by ANN, which is the orange, across all three fluxes. And compared to just for example, the core 3.6 algorithm. But for momentum flux, both algorithms are already doing pretty well. So the improvement is really, really minimum. Maybe in terms of bias, there is a reduction of bias. For sensible and latent heat fluxes, we could see that both algorithms have less correlation with the measurement. So it's harder to predict these heat fluxes. And the largest improvement we've seen is for the latent heat flux. in some areas, we're able to increase the R² by about 0.2, and we see a general reduction of bias as well. And this was also discussed by another data-driven RC flux paper, Zhou et al. 2024. They also noted that there seems to be a bias in the latent heat flux when you just evaluate it against the measurements in bulk algorithms. Yeah, but I haven't seen it discussed elsewhere, like explicitly. And also we wanted to point out that the score kind of vary across different regions of evaluation. So North Pacific, Atlantic, Southern Ocean, tropics. And this is because there are generally different inputs distributions from these regions in terms of wind speed, air sea temperature difference, relative humidity, etc. So there is actually kind of distribution shift across regions, and this is generally a challenge for data-driven model. But as we see, although the score fluctuate, the ANNN is able to kind of outperform a core over all regions. So that is for the mean. For the standard deviation prediction, so for the uncertainty prediction, we don't really have a truth to compare to. But we can take a look at the structure that the neural network predict. So here, we're basically taking a 2D slice across the input space. So it's visualized with varying wind speed and varying temperature difference. And the color shows the predicted standard deviation by the neural net. So we see generally at higher wind speed, especially about 15 meters per second, there's higher uncertainty. But also on the low wind speed side. And it's kind of asymmetric for positive or negative temperature difference corresponding to different stability regime. But also some of this predicted uncertainty comes from the data itself. The above 15 meters per second is so this density plot shows our data, and the above 15 meters per second regime is kind of undersampled. So some of this will contribute to the predicted uncertainty as well. But overall, the uncertainty structure seems reasonable, and this is also one of the strengths of this work is now we have an explicit representation of uncertainty, and it's also state dependent. And then we can use this for many kind of applications for uncertainty quantification, but also for stochastic parameterization. And this is just a quick overview of stochastic parameterization, and particularly for air-sea fluxes. And there have been works exploring it in the context of climate simulations, but usually the noise is added kind of ad hoc with, for example, a magnitude proportional to the flux itself, given by Williams 2012. And the hope is by having learned a representation of uncertainty that is state dependent, we could further refine this stochastic parameterization of air-sea fluxes. And we could use that to study if there will be a change in mean state and variability once we implement a stochastic representation of air-sea flux. And we first kind of demonstrated this idea in a setting that is pretty low cost, so a single column motion model. And this was demonstrated earlier by Alexei I hope, in the demo. And so here but in my work, I was running it in more of an offline version, meaning that I generated all the time series of fluxes and the stochastic ensembles offline, given the measured variables at Ocean Weather Station Papa, and I used them to force the single column. We could take a look at the time series of the flux at this particular site. And I think this gives us some insight of how the neural net is different from bulk algorithm. So here the blacks are two versions of bulk algorithm. One is core 3.06, one is the UNCAR algorithm. But you can see that the black lines almost overlap on top of each other, and you can only spot the difference when there are some extreme values, for example, the spike here. So they are actually pretty close, but the ANN is generally more different from both. And here the envelope shows the standard deviation predicted by the neural net. And the thin orange line shows the two samples of the stochastically perturbed flux, where the noise is added by an autoregressive process. And the other thing we wanted to point out is that seems like the bulk algorithm predicted fluxes, the black ones, generally fall within the envelope predicted by the neural network. So in some sense, we could interpret them as a possible ensemble members in this stochastic setting. So we run this both deterministically and stochastically. And there is a response in the deterministic version as well. But I think I'll just briefly go through it because I think the online implementation I later did an online implementation in coupled CSM, and it's probably more insightful to look at that. But here, what we observe is because we also did monthly restart of the simulation with a true temperature and salinity profile. Generally, there is not much of a change in the mixed layer depth. So the black and orange are the mixed layer depth in the ANN and in the control and the ANN. But there is some level of temperature difference within the mixed layer and on the order of a fraction of a degree. But we could, as a demonstration for how we could maybe use the stochastic version in this setting, here we are plotting the mixed layer depth and SST in the deterministic run by blue, and the magenta is the ensemble mean, and the shade is the ensemble spread. And if we kind of visualize the spread, so we don't observe a drift induced by adding noise, but we do observe an increased spread. And if we visualize the spread in color across different months, we see that the largest spread in ST is observed in the summer, where there's the shallowest mixed layer. This kind of makes sense. You have less of a buffer for perturbation of heat fluxes when mixed layer is shallow. And the largest spread in mixed layer depth occurs during spring restratification. So this kind of sudden events where it restratifies, the onset timing of this is kind of sensitive to the flux leading to that event. So yeah, just demonstration of using stochastically generated flux sequences in this an idealized 1D model. So for a summary, we know that there are uncertainties in RC flux algorithms themselves. I think we shouldn't just sweep them under the carpet because this is kind of hard to tackle. And we developed a probabilistic flux algorithm with built-in uncertainty quantification using observational data. And it has better statistical score and reduces the bias, especially we observed in latent heat flux. And we demonstrated the stochastic flux forcing in a single column model, which shows us a seasonal response. And a main takeaway in this first part is that we know that direct eddy covariance measurements of fluxes are very limited. This is kind of under the reason how we used very compact neural network. We've chosen a simple set of inputs to prevent overfitting, but they remain our best available constraints for IRC flux. And we have demonstrated that it is possible to learn a data-driven algorithm directly from these measurements, similar to existing bulk algorithms. But because we bypassed some of the assumptions in, for example, Mononabokov that may not always be valid, this gives us a perspective that we could use to look at possible biases in existing bulk algorithms. And this is in this manuscript. And I think for the last 5 minutes or so, I will go through some preliminary results of this, the implementation of this in a coupled CESM model. And the context is that people have been pushing for hybrid modeling, so dynamical numerical core plus machine learned parameterization. And this is in collaboration with YinCar CESM MLE integration team. So they are developing a machine learning enhanced version of the next generation of CESM. And they want to put a suite of machine learned or data-driven parameterizations inside CSM, and the ERC flux is one of the candidates. And the implementation is done using this Fortran PyTorch bridge called FTorch that was developed at ICCS. But they have kind of have a established pipeline for doing that now that allows you to call for a neural net at least written in PyTorch. And so I did this in a developing branch of CESM3. So this is already with MOM6 as the ocean model. And I did kind of 45 years of climate control run. So I have a control case and a neural network in which I've so far only modified the latent heat flux, because as we recall, this is where we see the most improvements from the neural network. And I've done it only deterministically. And we didn't observe any numerical instability, which is a plus usually with this machine learned algorithm. But it's, I think, because the RC flux tends to be down gradient, and it's generally not going to cause instability. And I've checked the global heat flux balance. So this is over the 40-year run. If I integrate shortwave radiation plus longwave radiation plus latent insensible heat across the ocean surface, the exact numbers here is subject to further scrutiny, but I think the main idea is in both the control and neural network, we see a similar level of imbalance. And it seems to have stabilized after maybe 10 years. And this is the spatial distribution of the latent heat fluxes. So colors are all blue because the ocean is losing heat due to evaporation. And when we look at the difference, red means that there's less evaporation. So this is the pattern of the difference that we see averaged over the last 10 years. So in terms of the SST response, we see a pretty large change in SST after 35 years. This is 10-year average. And a lot of warming, especially in the and this pattern doesn't really project onto the difference in latent heat flux. We also remark that there seems to be an evolving response. In the first 5 years, it was smaller, but then it gradually establishes. This is also, I tried to compare this with, for example, this previous implementation of different bulk algorithms in NEMO, but in a forced simulation, we observe different magnitude and different patterns. But it could be that in this Bonino 2022 paper, it was only run for 1 year and it's forced by ERA5. And here we have run the simulation for much longer and in a fully coupled climate model. And this is the winter mixed layer depth change. Again, pretty large response. In this particular version of CSM, there seems to be the problem of too deep convection in the North Atlantic in the wintertime. And this was mitigated slightly by the neural network. And in the summer, we generally observe a deepening of the mixed layer in the Southern Ocean. But also this response took some time to establish. For example, if I check earlier, 15 to 25, it's a slightly different pattern, or it's a different pattern, but the response in the Northern Atlantic and the Southern Ocean was already there. So in summary, these are pretty preliminary results, but given a latent heat flux difference, that is not that outrageous, I would say, because, for example, in the bottom is for context, a standard deviation between 11 flux products on an annually averaged turbulent heat flux. And except for regions outside the boundary currents, I think this is on the order of 10 to 20 watts per meter squared, and same for the online implementation. So this is generally within the uncertainty we have of turbulent heat fluxes, but it generated a very large response in SST in this coupled CSM. And we observed that depending on the field, the response took some time to establish, and the patterns also do not directly project onto the latent heat flux change. And the last slide is one of our guess for why this could be the case. I haven't shown any response in the atmosphere, but there definitely is. For example, here we're plotting the local coverage, and we see that in the Eastern Pacific, which are usually hotspot for low stratocumulus clouds, there is a reduction of clouds, and this can be seen in the shortwave radiation. So there is a reduction of cloud, increase in shortwave radiation, and this could contribute to the warming in these areas, and then the signal can be transported westward towards the west. And also the warming of SST in these regions will in turn trigger even less low clouds. So maybe it's because we've triggered this cloud feedback that we've seen such a large magnitude of warming. And this, again, will only be present in a coupled model. So yeah, the main summary for this part. So in these preliminary runs, we've seen that a change in latent heat flux alone can generate a considerable response. And it's much larger in magnitude in the forced single column run we had before. And the next step will be more analysis on the impact on the climate state and the variability, comparison with observations, etc. And I should say that this is kind of a framework for us to tackle the problem of uncertainty in RC flux algorithm, and we're not saying that this version of the neural net itself is perfect. It's subject to further iteration and calibration online. And also, we wanted to explore the use of stochastic parameterization in coupled CSM as well. And my acknowledgement for the help from the CSM MLE team and the CGD groups, which made this second part of the work possible. And I will take questions. Thank you.
Thanks a lot. Thanks a lot, Jiarong, for this talk. So we're not able to actually show you the audience here, but I see many smiles, but also say frowning faces, people willing to understand. So that's a good setting for questions and answers. I will leave the floor to Thierry for navigating in the room, and I will take the questions online. If you guys online have questions, please raise your hand as for previous sessions. Thierry, the floor is yours.
Questions? Mr. Brodo.
Hello, thank you for a very interesting and instructive presentation. I have a question. When you compare the result of your model to the COR 3.6 algorithm, have you computed the fluxes with COR yourself, or you just got them from the data set?
You mean in these ones?
Yeah, the one where you find there is a strong, quite a difference between on the latent flux.
Well, I used the ArrowBulk package.
Okay, that's a very good pick. Yeah.
I believe developed here.
Yeah, that's me actually. Laurent Baudot speaking. So yeah, that's why I'm really interested, and I jumped on the microphone basically. Just the discussion we had this morning, actually, with other people, with Gökhan and company about the fluxes. You know that. Can you explain us how you dealt with the confusion that often arises by the fact that COR is meant to be used with the skin temperature, because there is a cool skin and warm layer parameterization included that comes with COR. And sometimes people are not using that, they're just using the bulk SST. So basically the SST you would measure at 1 meter deep. And since the latent heat flux is extremely sensitive to the skin temperature, because that's what drives the evaporation, you know, the influence of the SST on the saturation of humidity at the very surface. I was wondering, can you clarify how do you stand with this, you know, confusion SST, skin temperature, and how do you think your model has taken into account all this? Sorry for the long questions.
Yes, I know what you mean. I've seen that option when calling core. Maybe I tried it at some point with both skin correction and not, but I think here I can't remember, but I think here I didn't use the skin correction. I will double check and let you know. Okay,
so that might be something to explore regarding the results you find on the latent heat flux, I think. But generally, that's great. I mean, a great work you're doing. It's really cool. Thank you.
Arne?
Yeah, thanks for a very interesting talk. I have a question on the databases for the neural network. I mean, you've shown that this is extremely sparse. And I was wondering, how confident are you that you are covering all the regimes? And quite related to that, you've calculated biases. What kind of independent data do you use then? if you have already a sparse data set for the training?
Yes. So here I plotted the bias across the entire data set. I have some independent test where I train on 80% of the data and test on the rest. But when I was training, I didn't separate data depending on geographical regions. We observed that by doing that, because it's so sparse, if you leave out any particular region, you end up with a worse algorithm. So I kind of need all of them, like randomly sampled.
But are the 20% that you omit and later use for the training, are these independent enough? If they are artificially sampled, because they could stem from, let's say, half an hour ago, or so not independent.
Yes. So in some sense, yes, some of this data is time series that are 1 hour apart. But I don't think there will be a leak that way, mostly because of the setting, how we are only learning on 5 parameters, sorry, 5 inputs. And our hope is that by selecting such kind of the minimal amount of inputs, we kind of eliminate the possibility of overfitting, because these are all very essential inputs. I tried to add more, then the data set, then the neural net starts to overfit. But here, these are absolute essential inputs, and we also did early stopping, etc., to prevent it from overfitting.
Okay, thank you. Very interesting.
Yeah, thanks for the question.
Other questions in the room? Steve?
Yes, Jiarong, very nice talk. I think you had a map, following up on this sampling or the data, do you have a map of where you had, I think, can you pull that up? Yeah.
This one?
Yeah, so that is pretty sparse. There's nothing, as far as I can see, in the Southern Ocean, am I right? Or is that something south of Australia?
So there's like gas exchange, the brown ones down here.
Well, I just to follow up, because you said that if you remove data, the answer changes quite a lot, the model changes quite a lot. Presumably, if you added some more data, it would change a lot as well, especially if you add stuff more in the high latitudes or the Southern Ocean where you have very little now. I'm just wondering, is there a way that when are you going to feel confident in what you've got? I guess when you take away data, nothing changes, or what's the strategy for this with such sparse data? It's not a very well formulated question, I admit, but I just wanted to get your thoughts on that.
Yes. So, well, there is this additional data set from buoys that we could potentially use later, also as an independent check for whether we have learned a reasonable thing. But here the problem is with these OOI buoys, they have only momentum and sensible heat flux, so there's no direct measurement of latent heat flux. So we have to think of ways to use this incomplete data set, which will require some method like transfer learning. Also, I think what gave me confidence is again this plot where I show both algorithms, although their scale really vary across different graphical regions, it's not like I'm seeing much worse from the neural net than the bulk algorithm itself in certain regions. So if that would, of course, there is still like a change of skills, really. So, but at least it's looking okay, like it's improving across different regions. And I guess the other thing is, or really for these online implementations, if we get something really unreasonable, we will go back and take a look at this. So it's still undergoing an iterative process. I don't know if this is a satisfying answer, but
Steve seems happy.
We have another online question by Fred Dupont, I think. Fred, if you want to jump in.
Sure. Yes. Thanks for the talk. A quick question about spatial representativity or uncertainty. Is that something you can account as well? The fact that the model is a spatial average versus the point based observation.
You mean kind of this work where you're referring to like this rectifying effects from over smoothed input field?
Yes.
Yes. I think they're trying to learn a representation to correct this, and it's undergoing work.
Okay. Thanks a lot.
Yeah.
Mike.
Yeah, thank you. Very, very nice talk. I'm wondering if I could ask a rather naive question, really, which is about the R squared values that you have, and for the latent heat flux, and particularly the sensible heat flux in the tropics, for example. Your R squared is what, 16% or something, and 40% for the latent heat fluxes. I'm just wondering, I mean, where does most of that come from? You know, why isn't it larger? What are the main sources of
this looks really bad, but so the R squared is kind of a normalized MSE. So it's mean square error normalized by the variance of the data itself. So actually, if I just plot MSE, it will be more comparable between regions, but because the variance, so the sensible heat flux values themselves are smaller in the tropics. So after normalization, you would see this really popping up as a poor R squared region. It's basically that our MSE is comparable to the variance in data itself. So it's capturing very little portion of the variance. But it's also because the variance in tropics is small itself. Does that make sense?
Mike says yes. Apparently. Other questions? I got one, by the way. Maybe I missed something, but you showed a limited impact on RC fluxes, but a very big impact on SST. I'm not sure I heard your possible explanations for that, and whether this decreases possible SST biases, if it goes in the right direction, basically.
Yes. So this was basically this slide, and we think somehow over some years, after some years of implementing this different latent heat flux algorithm, we triggered a cloud feedback these regions. So it's a positive feedback loop where when you have higher SST, you have less low cloud, and then you have more radiation from the sun, and it keeps warming. First, this is a little bit speculative at this point. I think it's because we think that maybe because of this, we're seeing such a large change in SST. Like, it's larger than this like purely forced Nemo run. In terms of whether this is in the desirable sign, yeah, I still need to compare the control with an observation, but I haven't yet done so, and I need to talk to people at NCAR to see which data set to compare this particular configuration to. Is
Okay.
It was also like a developing version of the CSM. So
Okay, thank you.
I think we do
yeah,
have
this
a.
was not expected at all that we saw such a big response.
So we have an online question by Anne-Marie Tréguier, please.
Yes, well, thank you very much for this presentation. So I'm not sure my question is relevant because maybe I haven't understood. Is it right that in your test with CSM, you change only the latent heat flux?
Yes.
And so my question is, why didn't you change also the other fluxes? And isn't it that there is some correlation maybe between like the latent and the sensible heat flux, so that you could have introduced, in fact, a kind of spurious artifact or something like that in the model that could explain why you have such a big response in the coupled system? Why didn't you also change the other fluxes?
Yes, I will do that. I will have another run where I change both sensible and latent heat flux. We did this mostly because the latent heat flux is where we saw the largest improvement from neural network. And also we see really something in the North Pacific Atlantic region. So so the bulk, we thought it might be biased towards evaporating too much. This is giving the negative sign of bias. So we were thinking maybe by evaporating less in these regions, we could correct some of the mixed layer depth bias in these. But yes, as you said, it would be more consistent to change all fluxes. Momentum flux, I'm not sure. Really, we kind of learned something very similar to bulk. So I don't know how much we would gain from changing that. But for sure, I would change both sensible and latent heat fluxes together in the next iteration.
Thank you very much.
Yeah, thanks.
And I actually have also a question, Jiarong. Thanks also for this. For this great and really nice study you've presented here. My question is the following. So, imagine we had like the possibility to deploy some extra buoys at sea measuring RC fluxes and parameters. There's a question of where we would deploy them, and right now the most natural way to approach that would be to actually deploy them where we know the fit is not good. So basically based on the estimate of the uncertainty that you provide.
Yes.
Still, now that we're able to actually produce ensemble, you're almost there at the stage where you could produce like ensembles of realization that would allow you to show like the sort of spread in the response. Maybe the region where it would be interesting to actually put extra measurements may not be the region where the uncertainty is the biggest, absolutely, but where the impact in the models would be the largest. Do you anticipate anything there, or do you have like any hints of where the spread would be the biggest in ensemble simulations with the stochastic parameterization?
Yes, well, it seems, first of all, very hard to get any additional observations. So I would say anywhere
Fair enough.
would be great. And also measuring the vertical profiles of certain quantities would be great. Like, I don't know enough about observations, but I don't know if it's in principle possible to measure the humidity profiles, because that may not be as described by Mon and Obkov, and this would help a lot, giving us insights of what is actually giving the vertical transport of latent heat flux. And yes, where the flux prediction is poor, also we could also think about sampling just the input space. So where there is really high wind speed, for example, in terms of where we might see the largest spread in models once we implement a stochastic version. Yeah, for now, I'm not sure, because the response I got in the deterministic run even was completely not what I would expect. So I don't want to speculate even further for the stochastic ones. But yes, if we could find other ways to constrain the ERC flux algorithm, this would be really cool. What I mean is going beyond just comparing with direct eddy covariance fluxes, because we know how hard it is to measure these fluxes directly. If we could have some setting where we could compare actually, for example, the upper ocean state and use that to constrain the fluxes, it would be awesome. But for now, it's really hard for me to think of a good setting where it's clean enough and it's only the fluxes that is changing the upper ocean, which we can use to like constrain the fluxes. So yeah, that's just a lot of thoughts, and thanks for the question.
Thanks a lot for all those questions. I think we're getting towards the end of this discussion, and we'd like to thank you again for this presentation.
Thanks for having me.